Okay, well, this is going to be a brief discussion of a key concept called duality about matrix Riccati equations, and both the matrix Riccati the algebraic matrix Riccati equation and the matrix Riccati difference equation. So here goes. It's going to be a connection between two problems that at first might seem unrelated, but it turns out they're intimately tied together. So the concept that we're going to be, the message that we're going to get is these matrix Riccati equations do double duty. They do double duty, like I'm saying right here. So here goes. So let's start with the Kalman filter. We'll remember that. We'll quickly go through the Kalman filter really fast. Kalman filter is going to be defined by a set of these objects: an A, a C, a G, an R, an X hat 0, and a sigma 0. Everything in sight is a matrix or a vector of comparable dimension. We have system star, which is a state space system, where X is a state. We could call it hidden state, and X is an n by 1 vector. We have this law of motion. This is our observer equation. Yt is a vector of observations. That's a linear combination of this hidden states plus a shock. The shock is IID, normal 0R. It's a covariance matrix. WT plus 1, as usual, is normal 0I. And our initial condition for the hidden state is it's normal with mean vector X hat 0 and covariance matrix sigma 0. That's the original state. The achievement, remarkable achievement of Rudolf Kalman was to associate with this original system star another system called star-star. It's come to be known as an innovation system. It's a representation for the same stochastic process Y, but it represents exactly the same thing in terms of, not in terms of W and V, but in terms of a new shock A. The A is called the innovation. It's the part of Y that can't be explained by a linear projection of Y on past Y's. So stare at this. And then X hat is the projection of what we don't see, X on what we do see, the history of Y's. And this is itself a linear state space system that's characterized by this set of objects, A, G, which we had before, a KT, and AT is a new shock, which is normal 0 omega t. Omega t is equal to R. It's a covariance matrix. It's equal to R plus G prime sigma TG, where I haven't told you what sigma t is yet. And the whole object of the Kalman filter is to compute the covariance matrix sigma t. And Kalman showed us how to do that. So first we compute sigma t with this recursion right here. We compute, from an initial condition sigma 0, we take the right-hand side and the various matrices and we form sigma 1. Then we take sigma 1 and we form sigma 2. So this equation is our matrix Riccati difference equation. Once we know the sigmas, we get the k's from this top formula. So this system star-star, dagger-dagger, is the Kalman filter. That's the review. Now we'll pause here and we'll kind of ask, does this remind us of anything in some loose sense? So the Kalman filter was a system that allows us to form estimates of a hidden Markov state recursively as more and more data come in. And it's basically a version of recursive regression. You can show that these ATs are realizing a Graham-Schmidt procedure. So look that up in Wikipedia. Okay, let's turn to some other equations. So I'm going to just write down mechanically now an equation. It's a different equation. It's going to be a matrix Riccati difference equation. And it's this equation right here. I'll call it Dagger, this system here. I'm going to call it Dagger. This whole system, which is a system in a P and an F. And if you stare at this, the equation for P will sort of remind you of the equation for sigma, but it's not the same. The equation for F will sort of remind you, it's got a J index, will sort of remind you of the equation for K, but is different. And let's start with that. The equation for K involves this thing right here, this matrix here, E, this matrix E, this matrix G, this matrix right here, G, sigma, G prime, that's just what we had up here. That was equal to omega T. That's the covariance matrix of the innovation to Y. So there's an inverse of that covariance matrix. That's telling you this KT is a regression of something on that covariance, on AT. This KT amounts to a regression of something on AT. And if you kind of come back up here and look at here, look up here, we can see this first equation of the Kalman filter is just a regression equation. And that leads us to think, well, what is this? Well, that must be a covariance matrix of something. And I'll leave it for you to figure that out. So the equation for sigma, the recursion there, that covariance matrix is going to appear here. And then some other covariance matrices appear here, here. And by the way, they're the same ones as here. So this is all about multiplying and inverting covariance matrices. That's what sigma is about. So if you look at this equation down here for F, well, it kind of reminds us of the equation for K, but it's kind of flipped around. And indeed, to see how it might be flipped, do the following. Stare at the equation for sigma and the equation for P, and then just notice if we took the equation for P and changed A to A prime, we change P J to sigma T, we change R to CC prime. We're all done here. We've already we changed B to G prime. Then they match up exactly. They match up exactly. And furthermore, if we did that, Fj would equal Ft prime, Kt prime. So this is kind of a story of putting primes in the right place. And these things match up. So why is that remarkable? Well, this equation, Dagger, came from a completely different problem than the problem that led to the Kalman filter. And in particular, the problem that led to the P and the F is down here. It's the linear quadratic dynamic programming problem, where the problem is there's a state space that moves like this, where ut is a control now. It's a control. There's an objective function which is a negative of xt prime r xt plus ut prime q ut summed over all t. And we want to minimize that because r and q are positive definite matrices. And the solution of that problem is a decision rule ut equals minus fxt, where f is the limit of these fj's. And the value of the problem is e equals minus x prime p x, where p is the limit of the pj's as j goes to infinity. So that problem, if you kind of stare at it, that problem involves no randomness. It's completely deterministic. There's no random variables. The problem with a Kalman filter is all about randomness. But despite that, these two problems are connected. And I'm going to just close with two remarks about that. This remarkable correspondence between these two sets of equations, Riccati equations, is called duality. And its practical use is, what it means is the matrix Riccati equation does double duty. It can solve control problems, linear quadratic dynamic programming problems, and it can solve, these are called filtering or prediction problems, hidden Markov models. The same math can solve both. And that's a big takeaway. And then the final remark I'll make is, you might ask why? Why are these connected? How on earth could these two different problems are connected? And the answer to that, I'm not going to tell you right now. I can tell you where to find it. The key thing is duality. This is actually related to, it's an application of the Lagrange multiplier theorem. And you could actually formulate the Kalman problem, getting the so-called Kalman filter. You can formulate that as Lagrangian. As you kind of take the Lagrange multipliers on those constraints and rearrange them, they quickly become a linear quadratic dynamic programming problem. And that was a very clever insight that I think Kalman had. But that's an advanced topic that you might pursue. But you don't have to pursue it in order to take advantage of this correspondence. So if you have one set of programs, you can solve both linear quadratic dynamic programming problems, and you can solve Kalman filtering problems.